Perfect. So hi everyone, and welcome to our next edition of the EDT Community Talks. Yeah, I will not introduce the EDT Community. I hope you all know us from the last years of doing these regular talks of experts on engineering digital twins. Today, our expert is Bentley Oaks. And in this edition, we still plan to have one more talk in June. We still have to get the final approval from the company, but if everything goes as planned, we will have one final industrial talk in this series before we will go into a summer break. But enough advertisement. Let's talk about today's speaker. Let's talk about Bentley Oaks and his talk, Systematic Digital Twin Reporting. So Bentley is an assistant professor at the Department of Software and Computer Engineering at Polytechnique, Montreal in Canada. And to summarize his work, he's working on model-driven engineering for knowledge engineering of complex cyber-physical systems. And that includes the verification validation of these cyber-physical systems using MD techniques and formal techniques, but also the engineering and reporting of digital twins. And assuming, Bentley, that today you will talk about how we can more systematically do reporting on these digital twins. And I'm very much looking forward to that. And with that being said, let me stop sharing and the floor is yours.
Sure, thank you. Let me get there. Move this, that's right in my way. Okay, are my slides okay? You can see?
Yes, perfect.
Yep. Okay, so thank you very much for this the nice introduction and for the invitation. I'm very happy to talk to you today. I think that this is a pressing issue that needs to be discussed in our community. So I just want to do just some brief slides just so that you know my background. I did my master's and PhD at McGill University. I did some work in video game AI actually for my master's, and then for my PhD, I did some model transformation verification. This was part of a Canada-wide project. So this is where I got into the formal techniques, the formal verification validation. It was actually with IBM and GM, and I did a research stay at GM. Then I did my postdoc in Antwerp with Hans van Gehulle, and continuing this V&V line of research, so doing some functional safety V&V, and this was really getting down into the co-simulation level. And then I started getting into digital twins. So one of the first, we were actually working on the DT design project, which has been fairly successful with many publications. And this is where it started with the experience reports and trying to improve the reporting of digital twins. Then I came back to Montreal, did my second postdoc, and I was working on domain-specific machine learning workflows, so an entirely different line of research. And I started getting into ontologies, working with NASA JPL, discussing their tool, OpenCaesar, which is a really great tool for creating ontologies. But I'm not going to talk about that in this presentation. And then I've been still working on digital twins during this postdoc and looking at model qualities. So now at Polytechnique, I'm an assistant professor in the Oaks Lab, and really it's about accelerating knowledge engineering for complex systems. What do we want to do? I want to take everything I know, my background, and combine it together and just say, how can we take, domain knowledge and use it to create digital twins for these complex systems and make them safer and better and more efficient. So the current focus of my research right now is accelerating and systematizing digital twin engineering. I think that there's still a lot we need to do. Okay, so what is a digital twin? Don't worry, I'm not going to spend too long on this part because I assume that you have the background for this. I always like to point to Andreas Fortman's the wonderful literature survey they did, 112 different definitions. So just to show a few of them here, it's just all these different definitions. And when I was teaching this in class, I scared my students and said, okay, well, now I'm going to take the next 3 hours and read them all in a monotone voice. But I show this just to say that there are all these definitions and they don't quite represent what a digital twin is. So let me give you mine. And to put it in one sentence, it's a dynamic virtual representation of a complex system for supporting its design and operation. But I don't feel that this captures what a digital twin is. The way I explain it to people is to say, no, no, no. It's a paradigm where the base is modeling and simulation, but then it goes much further. It's modeling and simulation, plus the visualization, plus all these multiple domains, plus it's this, you get into the timing and the temporal stuff, the real time, ahead of time, you're doing the data and control with an actual system. It's a source of truth for all these services that you have on your digital twin, where the services bring value to your physical twin. The digital twin also you put intelligence in there, so the human domain knowledge, you want to do machine intelligence and all those things, you integrate it all together. And then once you have this integration of all these different pieces, you keep expanding it and extending it as far as you can. You keep growing it. And I think for me, talking about this as a paradigm rather than a definition is much more productive in talking with people and having these discussions. Okay, so moving on to the systematic digital twin reporting, just to give a little bit of motivation, because I think it's important to motivate why we need this. So I don't think I need to talk too much and say that it's diversity of digital twins. This figure is from Ishvan David's paper on controlled environment agriculture with strawberries. There is this other digital twin, though it's more of a digital model of some light rail inside a city. This wonderful video, if you haven't seen this one, I highly recommend it. It's NVIDIA Omniverse, where they build a complete BMW factory inside the NVIDIA Omniverse. That screenshot there it's actually digital, and it's just, you look at the screenshots and you're like, I'm not quite sure whether that's real or not. So it's a fantastic example of a digital twin. And then there is this other example, and I'll put the links down here. This other example on the right of the Vancouver airport built within Unity, and then they have a little app. And you can see the passengers moving around and the security problems and things like that. So all of these, you can see there's different diversity, there's different loops, different temporal loops. There's nothing built yet in the real case. On one, you have cyber biophysical systems with the strawberries, and those have a different loop, and you can't really control the strawberries. And so there's so much diversity here. So I think what I want to hear whenever I talk to someone, whenever I talk to a researcher, it's just like I don't want to talk and argue about definitions. Say, is it dynamic and virtual? It's a model. How do things connect? I don't want to. I would rather talk about what a digital twin is and what it does for you. So whenever I talk to someone, my questions are, okay, you have a digital twin. What services does it provide? Is it real time? How did you engineer it? Like, what was the process? Because I'm a researcher, and many, many other questions. But I like to focus on this way and say, yeah, it's question based, right? Like it's not the definition, it's what have you built already? And another aspect of this is just, yeah, unclear info and reporting. So from this first paper in 2021, I was reading these papers and I was just like, no, like I'm missing essential information. I'm missing the answers to these questions that I want to know about because of the lack of standardization. So just as an example, I hope that everyone is familiar with the definition by Kritzinger. The difference between a digital model, a digital shadow, and a digital twin is the manual and automatic data flow. So for a digital shadow, from the digital object to the physical object, it's things are manually done, and in a true digital twin, if you want to call it that, from the digital object to the physical object, it's automatic. So to put it another way, is your digital twin doing something automatically on the physical twin? If so, then it's a real digital twin by the definition of Kritzinger. And I mean, we can argue about what is this, is this definition good? But I think for me, it's interesting because I really care about when you're talking about a digital twin, well, is it automatic or not? Right? If you think about the automatic collection of data, I think that that's a really significant difference. whether things are coming from a CSV file or they're coming from IoT. And I think for the other way around, from the digital twin to the physical twin, whether you're doing something automatically or not, I think that's actually very important. If you're not doing something automatically, then you say, oh, it's, then it's actually really just modeling and simulation. But if you're doing something automatically, then it's like, oh, okay, well, then you have to worry about, security. Ishvan has a nice paper on autonomy. How much autonomy do we give to a digital twin? And then you deal with all the legal constraints on that. For a company, it's difficult to get to that because you have to have that level of trust for digital twin. So I think that if you have that level of trust to say, okay, my digital twin is actually controlling my physical twin, that's a real level of maturity that I want to read about in a paper. So I think it's actually important to know the categories of a digital twin. So just as an example, this was looked at in our first paper. It's a very nice paper, digital twin driven human robot collaborative assembly. And they have all these very nice services. So it's a human working together with a robot arm. You have vision analysis. What can human see? What can the robot reach? What can the human grasp? And I think also what can the robot grasp? The programming of the robot and then the operation time. So it's really trying to integrate the human and the robot together. The problem is that from the physical side to the digital side, you can read this report and you say, it's okay, I'm getting the production, sorry, just let me move thing, production requirements, inventory data, and the robot data. That's no problem. But what we found when we read this is that we weren't quite sure what's going from the digital side to the physical side. And it's like, okay, you have the robot programming, but is this like automatically deployed? I don't know. Does it automatically stop the robot? I'm not quite sure. And if it's not automatic, then it's not a digital twin by Kritzinger's definition. And again, we can argue about, does it have to be a true digital twin by Kritzinger? But I think that knowing if these operations are automatic, I think it's interesting in both in the practitioner and the research point of view. So go farther into the acting as a researcher. Yeah, I care about the services, the technology, the models, the engineering milestones. Yeah, that's what I mean. The community series is all about, and the wonderful EDT.Conf is about gathering information and sharing this as researchers. So I want to know this. I want to see this in papers. I want to read, okay, what exactly was done and not being vague. Here I mentioned the ACM empirical standards, the case survey of reading all these papers and then taking the qualitative data and turning into quantitative data. If we had more explicit case studies in digital twins, we could start to do these higher level surveys and systematic literature reviews and say, okay, what are people actually doing in their digital twins? And we're not there yet. So that's what I want to do. I want to push this forward so that we can do further research. Okay, so that's the motivation. I hope everyone agrees with me that we need to make it more systematic, really. And so I'm going to move on to our proposal for the reporting framework. So the goal is to come up with some characteristics, and of course, there's no correct answer for this, but just to say like, okay, what are the characteristics that we would like to see reported and discussed in papers? Move towards some common language, textual and graphical. I mean, for me, it would be nice if we could start to agree on some terms and some representations, some visual representations. Though I know that my preferences are not others' preferences. And then the goal is not to say like, okay, like you have to do this. This is enforced. It's just guidance. I just want to provide this to others and then we can discuss it. And it's not to say like, okay, you have to have all of these because there's 21, so there's an awful lot. It's just to propose them and then to say to authors, yeah, they're very flexible. If you want to change them, if you don't want to have one, if you want to add different ones, but you feel free, and then we can propose and discuss a new version of the framework later. So again, constructive intention is to support improvement and not criticize DT researchers or their papers. I fully understand the pressures of both time and space in preparing a paper, that sometimes you don't have time, you don't have space to explain everything. So it's not to criticize, it's just to support. That's really the intention with this. Okay, so the first paper again was 2021, talking about the characteristics and then how all the components of a digital twin work together in a constellation. We looked at 5 DTs in a paper and a further 15 online. And what we found was that based on Kritzinger's definition, we actually had classification differences with some other papers. So they said that it was a digital shadow. We said, it might actually be a digital twin. And then the reverse, they said it was a digital twin. And we thought, it might be a digital shadow. So just in one little one snippet is really here's the insights and actions that we found in those papers, and in yellow was where we had a question where we weren't quite sure whether something was automated or not. Okay, so the second paper on the reporting framework was actually an extension of that one. So there's a lot more detail on the characteristics, and we applied it to an industrial digital twin of a smart clamp. So the smart clamp, when it's drilling, the piece vibrates. So the smart clamp uses a vacuum to actually hold it and compensate for that drilling. So it's an example. It's a full case study of a digital twin, just to say, okay, here are all the different characteristics of it. And then we also did some work on mapping the framework characteristics to asset administration shell. Sorry, just for the asset administration shell. This is just to say, like, okay, what characteristics are implicitly or explicitly handled by asset administration shell, just to get a sense of how this fits into the landscape. So this shows the smart clamp DT constellation. So on the right-hand side is the drilling machine system under study. And then on the left-hand side is the DT constellation. So this is the graphical format that we started with in the papers, just to have some way of understanding or just one view presenting the digital twin. And I mean, again, it's not complete, it's just a conceptual view of things. But what I like about this is that it shows the loop of things happening. What exactly is the interaction between the physical system on the right and the digital twin on the left? And then the conceptual architecture of the digital twin. So just to walk through it very briefly, coming from the drilling machine on the right, you get some data going there on the bottom arrow going to the left. That goes into the models and data at the base layer of the digital twin, and then that goes up into some enablers, which is those computational components, and then that goes up into usages. And we actually renamed the usages, we renamed them into services later. And then those services on the top layer, they provide some automatic actions or some insights to the operator. So our intention again is just to try to, I mean, you can't pack the DT into one figure, but hopefully try to give more of a sense of what your DT is and what it does. So from this figure, one thing that's immediately apparent for me is to say there are no automatic actions. So this is actually a digital shadow. It's not a digital twin. So it's very explicit from this figure. And another thing I like about this figure is to call this a constellation and to really think of this as a collection of models and data and computational things and different services. And you can see that even for a relatively simple digital, well, it's industrial, but it's not an entire factory, but moderately complex digital twin, you start to get these data dependencies and flow through the digital twin. And I think that that's a really important characteristic of them, is to say, like, oh, it's a combination of the things. It's a constellation of all these components together. Okay, so the third paper is the one from last year. There's a QR code. You can also find this on my website. I'm not quite sure if this is in the way. I'll move that over. Yeah, and this is a journal article, and it's using cooperative robotics case study. And again, it's another iteration of this reporting framework. So we talk about 18 fundamental characteristics and 3 cross-cutting characteristics for reporting these case studies. And what we did is we took 3 different frameworks from me, the one from Dalibor and the one from Jones, and then we systematically merged them together. And in there, we report the robotics case study, the mobile robotics case study, and incubator case study, just to show how this can be done. Okay, so I'm not going to go through this, but just to say merging frameworks, we extracted all the characteristics from Dalibor and Jones and from my previous framework, and then on the next one, we put them together and said, okay, well, these characteristics, that turns into this one. So for example, the system under study and the counterpart on the top row here, connected together with a physical entity, physical environment, and physical processes, and we turn that all into the system under study, and then we give a 1-sentence description of that. And yeah, so to return to the D2 constellation, just to make sure that this is clear, because this is I think that this is for me, this is where it comes from. Have your digital twin connected in a loop. So we have those services providing actions and insights to the physical twin and the operator, and then from the physical twin you get data over, and then you get the models and data and the enablers and the services there. So it shows you that loop. Okay, so to talk about the robotics case study from the journal paper. The robotics case study, it's 2 robot arms, and they do manufacturing of little independent assets where they do like a pick and place on that grid at the bottom. So there's 2 robot arms and 2 grippers. And then on the digital side, this is a visualization in Unity, but what I want to highlight here is the services. So what can the digital twin do? It does what if simulation, trajectory visualization, discrete work in space commands, and deviation checking. Okay, so to put this in a constellation, again, is from the paper. So we have the robot arms on the left, and then from there we get the positions, torque, force, and opening on the bottom. We have the enablers, the communication ones, just to give you a sense of the technology that's behind there. So that the data comes into the bottom orange layer, and the models, and we have the different models, like the kinematics models and the URDF models. Those go up into the neighbors level, which is DT Manager, Maestro, RabbitMQ, FMU, Robotics Toolbox, and Unity. And from there, we have the services on top, which is doing the working space commands, deviation checking, etc. And from there, we get the automatic actions, which is the move, open, close commands, positions, discrete positions, velocity, and force. And on the top, going over to the operator, we have real-time visualization, alarm of deviation, and visualization of trajectories. Okay, so that's a lot of detail. You're probably still processing that in your head. But what I want to, yeah, I mean, my hope is that we can start to create these figures and to say, okay, this is my digital twin. This is what it's doing. And for me, this is, again, this isn't the complete visualization. I'm sure there will be many iterations in the future, but it's just to start and to say, here's the conceptual architecture. Here's how the data flows through it. And here's like here's what's being communicated with the physical twin, because sometimes that's really missing in papers. Just as a side story, as part of my digital twin engineering class, I took the students through a paper, and I went through the reporting characteristics, and I said, okay, you have to extract everything from the paper. And then at the end, we went through them, and a lot of the answers were I don't know. And I was like, okay, but what's going to and from the physical twin? And they said, I don't know. I don't know what's in there. So we need this detail. This needs to be reported. Okay, so to talk about the characteristics, here they are all in one shot. Again, this is a very hard thing. to do in a presentation. It's hard to go through 21 of anything. I'll try to keep it as light as possible, and I should also check the time halfway through. Okay, that's okay. Yeah, so what we did, we have 18, the top 18 characteristics are essential. And I mean essential as in like essential as opposed to cross-cutting. So at the bottom, data ownership and privacy, standardization, and security and safety considerations. We thought that those were cross-cutting and not like an essential part of the digital twin. So I'll read them in a second. I'll go through them and I'll talk a little bit about them. We also took these characteristics and applied them to where they might first appear in the life cycle of the system. So is that the design stage, the realization stage, the deployment stage, or the operation stage. Just to give a sense of, when will you worry about one and when would you worry about the other. So to talk about the robotics example, before I talk about the characteristics, we have a summary. How should I say this? We have a robotics example with the two manufacturing arms. And what we did is for each characteristic, we provided one or two sentences in the table. And again, it's just a very short view. We just want to give an indication of what it is. So for example, I talked about MC6, merge characteristic 6, digital twin services, just to say, okay, the services are what if simulation, trajectory visualization, et cetera, et cetera. Twinning timescale on the bottom. It's on demand, periodic basis on incoming events, slower than real time, faster than real-time services. Okay, so our intention here was just to take those characteristics and just to provide a table for it and say, okay, how much detail can we get into this table? Of course, it's not enough. You also have to, in some cases, go further and again, if this is interesting information, I would encourage authors to include more text than just the table, especially for something like fidelity and validity considerations. We've heard about this. I read about this a lot, but people don't explicitly talk about it. So this is just a section from the journal paper. As for quality assurance, the validation of the flux cell DT has been carried out through experimental validation as follows. The motion speed of behavioral models has been tuned so they approximate to the actual motion trajectory. Okay, and there's more description of this characteristic. And that's for the validity considerations. And then looking at model fidelity, which is again another thing that people say, okay, my digital twin is high fidelity. It's just okay, but what do you mean by that? I really want people to describe in their papers, what do you mean by that? So here, some of the limitations in terms of model fidelity are as follows. Kinematic models do not include the kinematics of the grippers. Trajectory generation provides certain time behavior based on assumed motion speed, et cetera, et cetera. This is details for the robotics case. But again, what I want to see is tell me in your papers about fidelity and validity considerations. Okay. And when I read these as a reviewer, I'm not going to reject it based on this. It's just these are limitations of your project. That's okay. You only have so much time and effort to spend on it. But tell me how you know it's high fidelity. Tell me how you know that your digital twin is valid. I want to know that. I think it's very, very important. Okay, so that was looking at the framework. I'm just going to briefly go through the characteristics and I'll make my slides available later. So I have 6 pages on this. So the system under study is the physical twin of interest and the environment and everything around it. The physical acting components is like, okay, how does the DT act on the PT? Physical sensing is, okay, how can the PT give information to the DT? And then talk about the physical to virtual interaction. Tell me what's going on there. What's the data, any input events, what's happening there? Virtual to physical, tell me about the other side. What's happening from the DT to the PT? The data, the insights, the actions, tell me about that. The digital twin services, I want authors to be very explicit. What is the digital twin doing for the PT in terms of these higher level services? And this, sorry, I should also clarify that this is not like the microservices thing. This is closer to something like a business goal. Like for example, optimization, task planning, and visualization. I think that those are nice concrete services that the DT provides at the right level of abstraction. The twinning timescale. I think this is important. What's the timescale? Because if you're talking about optimization, you could say, okay, well, my optimization happens in real time, right? But if you're doing predictive maintenance, you could say, well, I'm scheduling something for next month. It's like, to me, that's a very different time scale. Yeah, and even for real time, it's like, okay, are you worried about like the nanoseconds, the milliseconds, or is it like, well, something will happen, within the hour kind of thing? These are different. Slower than real time, and then faster than real time. If you're doing what if simulations, then you have to be faster than real time, right? And then you might say, okay, well, we're predicting something in a month or 2 months from now. Okay, that's very valuable information. Multiplicities. So tell me, what's the organization? Do you have one physical system and one DT? Do you have one physical system and 10,000 DTs? How do these things relate? Life cycle stages. You have the system, and you have your digital twin, and it might have different services for different stages of your system. Okay, tell me about that. How do these things evolve over time? Digital twin models and data. I think that honestly, for this one, this is a very, it's just one characteristic, but this could really, really explode into many characteristics. Talk about your models, talk about your data, right? Like I, again, hopefully from the characteristic and the examples and the description, it's that gives you enough of a basis for authors to really go into the important detail. So just to dive into this one, for the flex cell for the robot arms, yeah, it's data models from DT schemas using the AAS mental model, structural ones of URDF, behavioral models of FMUs. The data is related to the robot positioning. Okay, that's good. This talks about the technology. It gives a sense of how things are constructed and used within the digital twin. Tooling and enablers. What's the tools? What's the enablers within the DT? How does the DT provide services? So you can see on the right-hand side there for the robot arm one, it's a lot of technology there, which is good because then we can talk about these things and say, okay, well, everybody in this domain is using these technologies, well, this person is using this technology. Digital twin constellation. This is the constellation figure. I would really encourage authors to come up with something at the same level of abstraction where you have that loop together and just show these different boxes and arrows and things flowing through and talk about what is orchestrating the digital twin. Yeah, are there scripts? Are you using a platform? Like how do things communicate together? Twinning of process and digital twin evolution. This is one that I thought is really, really missing in digital twin engineering. Um, and I was happy to see in the call for EDT this year talking about exemplars. It's not just about the digital twin itself, but it's also about the engineering process. And I think that that's super, super important because when you read a digital twin paper, it's you don't even know how long it took to build, right? It's just like, okay, like it's just, a course project. Did this take you 5 years to build? And for me, I want to know, what did you start with? What was the first service you did? Did you build a 3D model and you visualize that and then you built things, around it? Or did you start with a MATLAB Python model and start from there? What did you start with? Like, I think again, going back to the systematizing of the engineering process, we need to know these details. Yeah, so this characteristic is really focused on this. What is your engineering process talk about the milestones. And honestly, if you have previous papers, this is where you could cite and say, well, this happened, this happened, this happened. Yeah, that's for the flex cell, it has its own requirements, and then the 12 milestones, which are described in the paper, say, no, this was first, this was first. These are the services over time. So very, very important characteristic. Number 14, fidelity and validity considerations. I talked about this before. Describe, how do you know it's valid with respect to your real system? How do you know it's high fidelity? What does high fidelity mean for you? Where do you know it's low fidelity, right? An example here could be, well, I don't care about the nanometers. I only care about centimeters when I'm doing my positioning, or I only care about milliseconds. Or I'm doing, a training environment, so I don't care about having precise behavior. I only care about general behavior. I don't know. Again, it depends on your digital twin. I want to know these details. C15, the digital twin technical connection. Talk about these things. You're doing this technical connection. Go into the IoT details. The hosting and deployment. Okay, is it in the cloud? Is it local? Tell me. Insights in decision making. Yeah, things that don't have a direct effect on the PT. Tell me about this higher level. How is it interacting with the operators of the system? Is there anything that isn't automatic, but it's this it's probably a slower loop. C18, horizontal integration. What else is the DT communicating with? So are you communicating with, other databases, other servers? Okay, so apologies for the real list of characteristics. I'm just going to end with three more. These are the cross-cutting ones. So these aren't specific to one area of the digital twin, but we thought that these are just very cross-cutting to talk about. It's more about the project. So data ownership and privacy. Where does the data come from? Just to make sure that authors are considering this when talking about it, because um, yeah, it's very important to think about, especially as we include LLMs to in our digital twins, to think about, okay, well, who owns this data? Where's this data going off to? How is it connected? Standardization. This was actually recommended by a reviewer of the journal paper, just to be very explicit, to say what digital twin standards are you using, so that we can promote these, so that we know what aligns, and so that we can continue with the research. So in the robot case, FMI standard version 2, and then the AAS meta model. And the last one, security and safety considerations, the ethical, technical aspects. Is there any safety considerations? In the robot one, of course, the robot can hurt a person, but this is just to talk about the characteristic, and just to say, yeah, is there anything special? Like, what environment is it working? Is it working with humans? Tell us about these details. Okay, so that was the characteristics. Hopefully you had some time to think through those and to process those. And then one question that we talked about in class was to say, can you come up with any crucial missing characteristics? And one that I liked was to say, one that I heard from a student was to say, was a digital twin really necessary for this project, or could it have been done in a different way? And I thought that was very interesting to think about, yeah, the benefits of a digital twin, and to make that explicit as a characteristic. So I'm going to leave this discussion point for the comments here. If you can think of a crucial missing characteristic, please tell me, and I'm very happy to add it in. Okay, so that's the framework. The next question is, okay, how do you use it? And I just want to recap what I said before, and it's just to use those characteristics as a guideline, and just try to report on your digital twin as precisely as you can. If you have the space, put it in detail. If you don't have the space, put it in in a tabular form. Try to come up with something like the constellation, just to say what's the data flow to and from the digital twin. Again, nothing is set in stone. If you say, I don't like this characteristic, I will not be offended, and I will not reject your paper. If you're out of room, place a table in an appendix or online. Yeah, the table is you could probably squish it to about half a page. So yeah, put that in an appendix, put it online just for someone to read and to better understand. And for guidance, the journal paper has the flex cell in the prose form in detail and in the table, and the mobile robotics one in the table form. And you've probably seen a few times from the Aarhus, Cauda Gomez, the template incubator, that's also in there in table form. So examples of this. The digital twin book, which I'll show in a little bit, also talks about a ship digital twin that's in the older version of the framework, but just as an example. So to talk about that ship, because I think it's interesting to say here's a an example of a digital twin owned by the Norwegian University of Science and Technology for marine research and exploration. And I didn't want to grab all the characteristics, but just to show you how I think that this helps you to understand what does it do. We can talk about the services of this of the digital twin for this research vessel, which is actually out there on the seas. What if simulation, real-time visualization, estimate the effect of environmental disturbances, anomaly detection, and estimation of remaining useful life. So you can see on the bottom center there, that figure, the remaining useful life prediction is starting to head down. And you see that there's anomaly detection where you say, okay, the air filter is clogging. So hopefully from this already tells you, okay, this is what the digital twin is doing for the ship. Enablers, it's built on the open simulation platform. How does it act and what's the data transmitted? It uses cellular 4G, 5G with MQTT, and then the data channels on the right-hand side. So again, this is just a snapshot, a few characteristics of the ship, but hopefully it gives an intuition to say, okay, we can start to systematically report on this digital twin. And then, yeah, here are that other characteristic on the digital twin evolution to say this is where it started with. So you can see at the top one, 2019, estimating useful life predictions. Okay, that was the first service of the digital twin. And then it continued to evolve past that. Okay, to switch gears, talk about the future. I have a few projects based on this reporting work. And I think one of the most important one is just to say, proposing this and then for others to use it and to find out, where it works and where it doesn't work. I think that's the most obvious and important one. So what I'm showing here is from the digital twin engineering course. Because I'm the instructor, I have the privilege of I got the students to do course projects to create digital twins and to write reports about their digital twins. So of course I asked them to use the reporting framework. So this is an example of a robot arm, and in red it shows the robot arm where it's getting into the singularities where it can't turn anymore. And on the very far right in the top on the grid cube there, that's the deviation checking. So that was the dashboard they made, and then on the left it's their characteristics, system under study, action components, data transmitted, etc., etc. So this is how they structured their project course reports. And what I'm doing now is I'm reading this and I'm analyzing and I'm trying to understand what were the successful characteristics where they wrote what I expect them to? Where did they maybe miss the mark? Maybe they need a little bit extra example of extra examples, let's put it that way. I also have a master's project working on, yeah, what if we start to, not just have it as a descriptive framework, but can we start to make this prescriptive? And I just want to give a little bit of a glimpse of future work because we're working on it right now, and just to say, okay, can we start to generate visualizations or reports based on this framework? So stay tuned for news about that later this year. Okay, so just to finish up on the framework, and then I just have a few more slides after this. We really think that DT research and engineering is held back by incomplete reporting. So we offer 21 characteristics to report as precisely as possible as you can, and give you examples to learn from. So that's the journal paper from last year, and there's the QR code for you. And again, I'll provide my slides after. And I just want to talk about, again, the DT engineering course. There's the link there at the bottom. You can get to it through my website, bentleyjoaks.github.io DTE course. And what I did this morning was I put up the prod. I also got the students to do part of their reports. I got them to do 3-minute videos. So which actually goes through their course just so you can see. And I'm very happy that all of them had some visualization aspect to their digital twin. I think the beer fermentation one is in Unity, and I think the 4 on the right are all in Godot engine. Yeah, I really the students actually found that you need some sort of visualization in a digital twin just to make it look attractive. So I'm really happy that they came up with these YouTube videos. And then on the left is a book I was talking about. This is what based the course on, from John Fitzgerald, Claudio Gomez, and Peter Gormarsson, the engineering of digital twins. So it's nice. It really goes through all these different stages. The students found it very useful to read and understand to do this. Okay. To talk about, sorry, let me get the full thing. Yeah, some of the work we have right now. Carlos is working on recommendations of guided workflows. Leah is working on some empirical foundations in DT engineering. I have 2 open PhD positions on consistency in digital twins and on quality of digital twins. The master's level, Kieran is working on this digital twin reporting. Gabrielle is going to start on digital twin quality during model evolution. And I have a master's position open in domain-specific machine learning workflows. And then I'm very happy to have a MyTax Global Inc. research intern, Angelica, will be working on digital twin using LLMs over the summer. Okay, so to finish up, because I think I'm right on time, digital twin reporting and engineering must become more systematic. I think that's one of the things that that I really believe. And there is lots of opportunity from the model-driven engineering background that I have to start to use models. How do we use models? How do we use ontologies to structure digital twins and structure their reporting? I think it's a straightforward, maybe not straightforward, but it's and I don't want to say obvious, but it's I don't think it's a hammer looking for the nail. I think it's a very appropriate thing to do. It's to say, how do we structure this, and then how do we'll use that information to structure DTs and their reporting. So I'm very open to questions. Thank you very much.
Thanks a lot, Bentley. Let me stop the recording.